Hello everyone, I am Sanjeev and welcome to the third presentation in section 2 of CCO 1011. So in this presentation I am going to discuss the rate of convergence of the gradient descent methods, and this rate of convergence depends on the condition number of the alpha sublevel sets where alpha is close to the optimum value of the function, and which is also the condition number of the Hessian of the function near the optimum solution. So that I will cover in this presentation. So in this presentation I am going to discuss only those topics that are practically relevant and the idea that will carry forward in the Newton's method. So the main idea, the central idea is that the rate of convergence depends on the condition number of the Hessian of the function near the optimum solution. And Newton's method utilizes this fact to find to boost the rate of convergence. So in the first presentation we have discussed that there's an upper bound and there's a lower bound on the Hessian of the function, and this comes from the strong convexity assumption over the function fx. So we have assumed that our function fx is a strongly convex function, and we have obtained the lower bound, which says that del square fx is, or the Hessian of the function is greater than equal to mi and is less than equal to capital M times I, where I is a identity matrix of appropriate size. And we have derived that the upper bound on the condition number of the Hessian of the function is given by m over m, and the condition number of the alpha sublevel sets where alpha is very close to p star, where p star is the optimum value of the function, that is f of x star, and as alpha tends to p star, the condition number of the alpha sublevel sets is a condition number of the Hessian of the function near the optimum solution. That is, the condition number of the alpha sublevel sets where alpha is close to p star is equal to a condition number of the Hessian of the function f at x star. So this all we have discussed in the first presentation, and we have also discussed that the alpha sublevel sets is the sublevel set is an ellipsoid centered at the optimum, and therefore the condition number of the alpha sublevel set is the condition number of the Hessian of the function at the optimum, which is an ellipsoid centered at x star. So this is an equation of the ellipsoid, and the ellipsoid is centered at x star. So this is our general descent algorithm. So what we do in descent algorithm is that we choose a starting point x0, and the starting point x0 is chosen such that it belongs to the domain of the function. So if a function is a convex function, then the starting point is really not a big deal, because no matter what starting point you choose, you will finally end up in the global minima. But suppose if your function is a non-convex function, so in a non-convex function there can be several local minima, and what local minima your algorithm is going to find depends on the starting point of your algorithm. Therefore, choosing the starting point in a non-convex problem is a very important thing, and if you have some prior knowledge about the function, then it can really be helpful in finding a better local minima. Therefore, the starting point in non-convex problem plays a very important role, and the descent algorithm proceeds as follows. We just repeat these three steps. We first find a descent direction, which is delta x, and then through the line search methods, which can be exact line search or inexact line search like backtracking line search, we choose a step size or the step length t to move in the direction delta x, and then finally we update our x, where x takes the value x plus t delta x, and we repeat these three steps until some convergence criterion is satisfied, where convergence criterion is nothing but the norm of the gradient of the function. If the norm of the gradient of the function is less than some pre-specified value, then we stop this algorithm. So here is a gradient descent algorithm. In gradient descent algorithm, our descent direction is negative of the negative gradient of the function, and we choose a starting point such that x naught belongs to the domain of the function, and we specify a small value epsilon, which is a small positive constant, and we take the descent direction as negative gradient, and through line search we decide the step size or the step length t to move in the direction delta x, and then finally we update x so that x takes the value x plus t delta x, and we repeat all these three steps until the norm of the gradient of the function is less than epsilon. If now the gradient is less than epsilon, it means that we are very close to the optimum solution. In fact, we have found the epsilon suboptimal solution. So now we will focus on the rate of convergence of the gradient methods using the exact line search and the inexact line search. So here I will derive the result for the exact line search, and the derivation for the inexact line search you can look in the book chapter 9 of the convex optimization, and the exact derivation is not that important because the central idea is the main thing, that is the rate of convergence depends on the condition number of the Hessian of the function near the optimum, and this is the only important thing that will be used in the Newton's method. But it's always good to look for the theoretical details of the rate of convergence, and therefore you can go to the book Convex Optimization to see the theoretical details of the derivation. So from the first presentation we have this S, which is the sublevel set, a closed sublevel set where S is a set of all x belonging to the domain of the function such that fx is less than or equal to f of x0, where f of x0 is the initial starting point. So this inequality holds for all x and y in S. I have discussed in the first presentation. This comes from the strong convexity assumption where the Hessian of the function has an upper bound m times I, and the update rule is that xk plus 1 is xk plus t delta x, where delta x is negative of the gradient for the gradient descent methods. So substituting y equal to x minus t times gradient of function f in this inequality will give us this function f tilde of t, where f tilde of t is a function of t, which is f of x minus t del fx. We just replace y with x minus t del fx, and the resulting function we call that f tilde of t, which is less than or equal to fx minus t times square of the norm of the gradient of the function plus m times t square over 2 times square of the norm of the gradient of the function. So we have this inequality, and in the exact line search method the next x, that is the xk plus 1, is xk plus t exact times delta x, where t exact is the value of t that minimizes the right hand side, and the right hand side is a convex quadratic function of t, and therefore differentiating the right hand side or differentiating this function f tilde of t with respect to t and equating the result to 0 will give us the value of the t that minimizes this function, the right hand side. So as I mentioned in the exact line search, this t is given by minimizing the fx, the f of x plus t delta x with respect to t, and the xk plus 1 is going to be xk plus t exact times delta x, where delta x is the descent direction. So the fx, so the f tilde of t is a convex quadratic function, therefore differentiating this function with respect to t and equating it to 0 will give us the value of t which minimizes the right hand side. And differentiating this function is not very difficult. Del over del t of fx is going to be 0 since there is not a function of t. Del over del t of this expression is going to be square root of the norm of the gradient of the function, and the derivative of this expression with respect to t is going to be m times t times square root of the norm of the gradient of the function, and equating the resulting expression to 0 will give us the value of t as 1 over m. So t is equal to 1 over m, and substituting this t in this inequality will give us f of x plus, or the f of FTD of t exact is going to f of x minus 1 over 2m times square root of the gradient of the function, where we have replaced this xk plus 1 with x plus for just single iteration. So f of x plus is going to fx minus 1 over 2m times the square root of the gradient of the function. And subtracting the p star from both sides, where p star is the optimum value of the function fx. So subtracting p star gives us f of x plus minus p star is equals to f of x minus p star minus 1 over 2m times square root of the gradient of the function. And in the first presentation we have derived that square of the norm of the gradient of the function is greater than or equal to 2 times m times fx minus p star. So substituting this in this equation will give us the inequality, which is f of x plus minus p star is equal to 1 minus m over m times fx minus p star. So it means that if we are at x, suppose at iteration k we have f of x minus p star, then f of x k plus 1 minus p star is going to be less than or equal to 1 minus m over m times f of x k minus p star. And applying this recursively will give us that f of x k minus p star is equal to 1 minus m over m to the power k f of x0 minus p star, where f of x0 is the initial value of the function, the value of the function at x0. So at iteration number k we have reduced the initial difference between the starting point and the optimum value with a factor of 1 minus m over m to the power k, where 1 minus m over m is going to be less than 1, since m over m is a small positive number. So replacing this 1 minus m over m with c gives us f of x k minus p star is equal to c to the power k times f of x0 minus p star, where c is less than 1. And the rate of convergence depends on this condition number, because the c is a function of m over m. Therefore if we decrease or if we increase capital M over small m, this capital M is always greater than small m. Therefore the minimum value of capital M over small m is 1. So if we increase the capital M over small m, that is, if we decrease the small m over capital M, then this number will approach to 1, and therefore the convergence will be slow. And if the capital M over small m is approximately equal to 1, or if it is slightly greater than 1, say it is 2, then the small m over capital M is going to be 0.5, and therefore the convergence would be very fast. It would be 0.5 to the power k. So that would be a very fast convergence, and therefore this shows that the rate of convergence depends on the condition number of the Hessian of the function near the optimum value, or we can say that it depends on the eccentricity of the sublevel sets. So this was for the exact line search method, and for the backtracking line search method similar kind of result holds. So in the second presentation we have discussed that the step length in the backtracking line search approximately minimizes the function f of x plus t delta x, where t is approximate of f of x plus t delta x along the array x plus t delta x, such that t is greater than or equal to 0, where there is no operator like approximate. So this is just to denote that the t approximately minimizes f of x plus t delta x. And the backtracking line search depends on two parameters, alpha and beta, where alpha takes a value from 0 to 0.5 and beta can take any value in 0 and 1. Generally the value of beta is kept 0.7 or 0.8 or 0.9. So in the backtracking line search, the exit conditions that f of x plus t delta x is equal to fx plus alpha times t times del fx transpose delta x. This already we have covered in the second presentation, so you can go back to the second presentation if you have any doubt. And the similar kind of result that we have discussed in the exact line search is applicable for the backtracking line search, where f of x k minus p star is equal to c to the power k times f of x0 minus p star, where c is 1 minus minimum of 2 m alpha comma 2 beta times m over m. So as we can see, this is not totally dependent on the condition number, but in one part it is dependent on the condition number. So the ROC, the rate of convergence, is at least in one part dependent on the condition number, and therefore the as capital M over small m increases, that is as small m over capital M decreases, then the rate of convergence also decreases. So for the higher rate of convergence, the capital M over small m should be nearly 1, or the sublevel set should be isotropic. And we will see this practically in the example. So here again we'll consider the example that we have discussed in the second presentation, that is fx is equal to x1 square plus gamma times x2 square, where x is in R2, and different gamma will give us the different eccentricity of the sublevel sets and therefore different condition numbers. So let's analyze this function. And so in this experiment, the value of epsilon, that is the exit condition, is 10 to the power negative 6. The value of alpha is 0.3 and the value of beta is 0.8. And the gamma, the values of gamma that we are choosing are 0.05, then 0.1, and with the difference of 0.1 we choose the values up to 20, that is 0.1, 0.2, 0.3, and we are plotting the value for, so we are plotting for the gamma equal to 0.05, for gamma equal to 0.1, for gamma equal to 0.5, 1, 5, and then 10. So let's run this. So we are plotting for the 5 values of gamma, gamma equal to 0.05. The starting point is 10, 1. So here the starting point is 1 and 10. And as we can see, if the gamma is 0.05, then the number of iterations required to find the solution are 211. So that's a huge number of iterations. And as we can see, the movement in this direction is very fast, whereas the sublevel sets are not isotropic, and therefore the gradient always points in this direction. If we take a gradient at this point, then it will point approximately in this direction, and therefore the update in this direction is very small, and therefore we can see that most of the iterations are the updates in this direction, whereas after this step I think that there's no update or very slight update in this direction, in the x direction. So as we increase the gamma, when gamma is 0.1, then the number of iterations are reduced, the number of iterations are 110. So the update in this direction, this y direction, would be higher than the update in case of gamma equal to 0.5. And choosing the gamma equal to 0.5 gives a better number of iterations. The 19 iterations are required, and with gamma equal to 1, just one iteration is required, since if gamma is 1, then the sublevel sets are circles, and therefore in a circle the gradient will always point towards the center, and therefore just one iteration is required to find the solution. And as we increase the gamma, for gamma 5 the number of iterations are 40, and for gamma equal to 10 the number of iterations are 82. And this is the final curve showing the number of iterations versus the gamma. When gamma is 0.05 the number of iterations are 211, and as we take gamma equal to 20 the number of iterations are nearly 175 or 160. So this is what we have analyzed for gamma equal to 0.15. So this was a plot of gamma versus the number of iterations, and the final conclusion is that the convergence depends greatly on the condition number of the Hessian or the eccentricity of the sublevel sets. So thank you for watching this presentation, and Searching has launched MacX, which is a combination of machine learning, reinforcement learning, and convex and combinatorial optimization. And soon we are starting the 1 week project, and anyone anywhere in the world can join this 1 week project. And the information will be soon released on MacX, so do watch the website for MacX. Thank you. I'm Sanjeev from searching.com.